Development and finite element analysis of heavy-duty sorting conveyor for agriculture. Application. Abstract. The present work deals with design development and finite element analysis of conveyor system useful for grading and separation of tomatoes for farming applications. A two-stage conveyor that separates tomatoes based on grade and size has been designed. This separation improves the financial yield of the farmers. Material selection of the conveyor components has been carried out using Ashby Charts. Computer-aided models of components are prepared using SolidWorks software. Solid modeling has been carried out considering dimensional aspects. Finite element analysis has been carried out using ANSYS Software. Static and modal analysis of the conveyor components has been carried out. Stresses obtained from static analysis are in close correlation with the available literature. Natural frequencies are devised from free vibration modal analysis. Mass participation factor evaluations for base and trolley frames are presented in this work. Present conveyor design shows improvement in performance over traditional ones. Keywords: roller conveyor, finite element analysis, modal analysis, material selection. Introduction. With the advent wheel, humans have been immensely benefited. The growth in all sectors was impacted immensely in production and financial aspects. Industrial revolutions that started between 1830 to 1840 were accelerated due to this invention. Industries that possessed land in acres or hectares for operation, employed labor for transfer of material from one place to another with the working site. This consumed considerable time and consequently affect production rate. The development of conveyor system began in 1892 for transfer and handling of material within the industrial unit. The conveyor system saved substantial amount of time and effort and enhanced the production rate. For industries with hazardous environments, the conveyor systems resulted into reduction of workplace risks. Different stages of conveyor development and gradual change in design as needed has resulted into the systems that are available today. A conveyor can be designed for a specific product or material handling. Abhishek v. Yenpure. Department of Mechanical Engineering, UMCO, Pun. Purva b. Todmal. Department of Mechanical Engineering, UMCO, Pun. Anand Biz. Director, Mech Tall Product Engineering Solution Private Ltd. Trough belt and magnetic belt conveyors, gravity roller conveyor and powered roller conveyor, wheel, chain, and slat conveyors. In present work, design, development, and finite element analysis of powered roller chain conveyor for tomato separation unit has been carried out. The design has been carried out with the use of Conveyor Equipment Manufacturing Association, CEMA, standard. The design phase includes material selection with the use of Ashby Charts, evaluation of component dimensions with the failure of theories and simulation of the component behavior using finite element analysis technique. Components of the present system include feeding and rejection conveyors, base and trolley frames, drive rollers, motors, frames supported on caster wheels, plates, take-up assembly, and trays. The roller assembly includes a roller guide passing through the roller and is attached to the angle sections mounted on chain which rotates the entire assembly. The frames and frame components are secured using bolted joints. Overall length of the assembly is 7,000 mm and the load carrying capacity is 2,000 kg. Self-weight of the entire conveyor assembly is 2,224 kg. The conveyor is powered with the use of a chain drive mechanism wherein the sprockets are mounted on both the ends and are coupled with a single continuous roller chain. Sorting operation of farm yield, i.e., tomatoes, occur with respect to their sizes. When the feed conveyor is loaded with tomatoes, first stage sorting occurs at this instant itself. The pitch of rollers on first stage feeder is 38 mm, hence tomatoes of diameter smaller than 38 mm are unable to continue their journey and pass through this gap and are collected at the bottom. The tomatoes of larger diameter that remain on the conveyor during first stage are carried upward to the for second stage sorting. The roller pitch in second stage is 47 mm, and hence tomatoes with size of 47 mm or larger will be sorted for further packing and tomatoes of smaller size are collected in the tray attached to the trolley frame. The present system has been designed to be semi-automatic and hence manual intervention is needed to remove the tomatoes collected at the base and trolley frames. Purpose. The conveyor systems are classified as flat belt. 2. Material selection, CAD modeling and finite element analysis of conveyor system. Material selection in present work has been carried out using Ashby Charts. Material conforming to the component performance under stipulated loads has been selected. Adopting the material selection process from Ashby Charts, material for shaft, frames, and rollers has been selected. Performance index, for strength, is of paramount importance in material selection, and hence material with highest performance index has been selected. In present application, the drive shaft is subjected to a combination of transverse load and torque. The load magnitude is 6.67 knots and torque magnitude is 95 Nm. Permissible deflection for this load-torque combination is the deciding factor for the material selection, and hence Young's modulus versus density chart is opted for selection of material for shaft. In similar manner for frame strength versus density chart has been used. For chain selection, IWIS standard has been adopted. Computer-aided model of the conveyor system has been prepared using SolidWorks software. Accounting for geometry of individual components, solid models of individual components has been prepared. These solid models are further given constraints of orientation and alignment from assembly considerations. The computer-aided model of conveyor system along with stage 1 and stage 2 rollers, input, feed, and output locations, base and trolley frames, caster wheels at the base, take-up device, and electric motor are shown in Figure 1. Behavior simulation under stipulated loads for trolley frame, base frame, drive roller, and shaft has been carried out using finite element analysis technique. The finite element analysis has been carried out using ANSYS software. In pre-processing stage, the step files of conveyor components are imported into S environment. The imported models were further verified for surface or geometry losses and other associated import errors. Meshing and application of boundary conditions and assigning of materials has been carried out in pre-processing stage. The trolley and base frames are meshed using beam elements. Total number of elements for trolley frame are 440 and nodes are 449. For base frame, total elements are 496 and nodes are 506. Material selected for both the frames is SCM 435, has yield strength OF350 MPa and Poisson's ratio of 0.29. All the 6 degrees of freedom of the nodes at the caster wheels are arrested and load are imposed at the load locations on both the trolleys. On the base frame, a total downward force of 25,277 N has been applied, equally distributed over 14 different locations on top members. The CAD and meshed models of base frame are shown in Figure 2. Fig 3. Base frame model with boundary conditions and stress plot. For trolley frame, the material properties are same as those of base frame, difference being the magnitude of load applied and the number of load locations. The load magnitude of 20,050 N has been applied at 30 different locations distributed equally at the load locations on trolley frame. The computer-aided and meshed model of trolley frame is shown in Figure 4. Are 9,151 and nodes are 18,327, while for the shaft total elements are 8,151 and nodes are 13,591. Material for drive roller is plain carbon steel with yield strength of 220 MPa and corresponding Poisson's ratio is 0.28. Material for the drive shaft is EN24 with yield strength of 470 MPa and corresponding Poisson's ratio of 0.285. The computer-aided and meshed model of drive roller is shown in Figure 6. Fig 6. Computer-aided and meshed model of drive roller. The rollers are attached using bolted joints to the frames. At both the extreme ends of the roller, fixed support constraint is applied which correlates with physical situation of roller fitment. A force of 2,420 N has been applied on the entire roller. The finite element model of roller with boundary conditions and stress plot is shown in Figure 7. Results of finite element analysis of shaft are mentioned in the succeeding section of results and discussion, however the models of same are avoided. Fig 7. FE model with boundary conditions and stress plot. To predict the vibrational traits of base and trolley frames, free vibrational modal analysis has been carried out. For both the frames, 4 mode shapes and corresponding amplitude displacement with associated frequency has been analyzed. Figure 8 shows the first 2 mode shapes while Figure 9 depicts the third and fourth mode shapes of base frame. Figure 10 and Figure 11 shows the 1st and second and third and fourth mode shape for trolley frame, respectively. 3. Result and discussion. The finite element analysis of the conveyor components has been carried out to simulate their behavior under stipulated load conditions. From finite element analysis, stress, displacements, and factor of safety shaft, drive roller, trolley frame and base frame are evaluated. These outcomes are summarized in Table 1. Table 1. Summary of finite element analysis results. Component factor of safety displacement, mm, stress, MPa. Shaft 2.490.795 189. Drive roller 1.866 1.1617 117.77. Base frame 2.320.895.2. Trolley frame 2.793.64 The maximum value of stress 189 MPa is observed in drive shaft, which is attributed to the collective action of torque and uniformly distributed force on it. However, corresponding factor of safety value is 2.49 that signify safety of shaft design. The stress value observed in trolley frame is 125 MPa and corresponding factor of safety value is 2.79. The stress value is far below the permissible stress value of 350 MPa. Maximum displacement is also observed in trolley frame. Additional stiffener plates are suggested to be welded to enhance the stiffness at the central portion. From modal analysis, the mode shapes and frequencies are evaluated. In addition to this, mass participation factors in X, Y, and Z directions are devised for base and trolley frames. The mass participation factor signifies the amplitude of displacements corresponding to each mode shape. The magnitudes of mass participation factors in X and Z directions for base frame are negligible as compared with those in Y directions, while for trolley frame the magnitudes of mass participation factors are considerably increased, however still their magnitude remains less than those in Y direction. The outcomes of modal analysis for base frame are summarized in Table 2. Conclusion. Following are the inferences drawn from the design and finite element analysis. 1. A two-stage sorting conveyor mechanism for grading of tomatoes based on sizes has been designed. This mechanism is helpful to grade the tomatoes based on size, which will increase the income of tomato farmers, as tomatoes of same size are sorted. 2. Concrete base for material selection using Ashby charts for components of the conveyor has been established. The said conveyor is proposed to be manufactured as put into service. 3. The values of factor of safety and the magnitude of stresses induced in the shaft, drive rollers, trolley, and base frames fall in safe zone. 4. From modal analysis of trolley and base frames, it is observed that the maximum frequency of 116.79 Hz occurs for fourth mode and corresponding displacement is 0.284 mm for base frame. This is attributed to the position, orientation, and overall combination of base frame members. 5. For trolley frame, the maximum value of stress occurs at the bottom members. This indicates effective load transfer through every individual member. 6. For drive roller, the maximum stress is observed in central portion, which is attributed to the simply supported beam behavior of drive roller. 7. For base frame, the frontal tapered portion and corresponding members are subjected to stress. This is attributed to the geometry of the conveyor system. The stresses induced are within permissible limits.